Go. Yay. All right. What are we going to do today? Well, hopefully, I won't tax your brains quite so hard today. Whenever we have a couple classes together, I guarantee you one of them will be programming heavy and the other one won't. So this is not the programming heavy one. Hint at what the other one will be. Today we're going to take it up a step. Last time we talked about assembly language, we talked about machine code, we talked about how your actual computer boots and starts. The next step in that evolution is, what's the main application that you're running on a day-to-day basis? And the main application that you're running really is your operating system. And in our case, that's typically Windows. So with Windows, what exactly are we getting our operating system to do for us? And that's what we're going to dive into a little bit today. What's the main purpose of that operating system? So we're going to talk about a couple things that it does. The big ones are listed here. The first one is preemptive task switching. So the ability to run multiple programs and to manage and organize that. The second thing that the operating system does for us is it manages all those system resources. When we're working on applications, we have to realize that we're not the only program running on the computer. And as much as games like to think they are monolithic things that are the only ones running, they're not. There's stuff running in the background all the time. We need to understand what those things are and how they affect our programs. And then we're going to do a little bit of memory work to kind of get ourselves heads wrapped around the idea that a lot of the resource that we really play with is memory in the computer. We can't actually make a computer go faster or slower. We can't necessarily make the computer operate differently in terms of graphics or the capabilities it has, but the two things we can generally affect in our programs are how much system RAM can we use and how much hard drive space do we use. So we'll get into a little bit of that. Now, the biggest thing that we do, or our operating system does, is it manages our basic system resources for us. It's there to provide an environment for us to build and run applications. And those applications could be editors, and those applications could be tools. They could be our game engines. They could, in fact, be the things that let us stream or anything we can create or dream up. And the operating system's job is to make sure that if you run multiple things at the same time, that they don't step on each other's toes. So we got to figure out how it's going to do that. And the reason we want to know is there are times we're going to be building tools, and we want those tools to share nicely with the rest of the operating system. And there are other times where we're going to be building games where, for the most part, we want to take over the graphics part of the computer, and we want to have as direct access as we can, but we don't necessarily want to take off the whole computer. So we want some things to be able to operate in the background. We're also going to manage a lot of our storage there. And there's this one kind of idea that's going to recur with all the applications we build over the course of the year. And that is, when you're trying to make things run a certain speed, one of the things you can do is to trade space for speed. As we looked at the hardware architecture last time, it's not hard to imagine that the physical distance you have to make data travel will make it faster or slower. So the distance from the CPU to the level 3 cache on the CPU chip is the shortest. So it's also the fastest. It's also the most expensive. So that cache the CPU takes care of using on its own. It caches the last few instructions that were sent to it, so that if you do those instructions repetitively, they don't have to travel that far. The next closest thing is your system RAM. Again, faster than anything else, but a little bit farther from the CPU. Farther from that down the line is your hard drive or your solid state drive. Farther than that down the line is anything on an external device. Farther than that, things like USBs and SSD sticks, memory sticks. And farther than that would be out on the network. And all of those things have increasingly larger capacities at farther and farther distance. So as we build applications, knowing how quickly our operating system can access information can help us figure out how we're going to structure our application. Try and imagine building a game where the amount of space that the environment that the player is playing in takes up more RAM than the machine physically has. And what do you do? And if you think that doesn't happen very often, I would suggest you try playing any large open world game. Everything from Red Dead Redemption to Death Stranding to Skyrim to, you choose it. Those large open world games use more RAM for their environment than physically exists on the consoles they run on. So the operating system has to do something to manage that. In a game console, you have to write it yourself. And how we break apart the different parts of the data in our application is largely dependent on what operating system we're playing with. Now, we looked at it last time. The operating system on our Windows computer really just takes care of booting the computer, managing basic I/O. That's all the interrupts for your mouse and your keyboard and your gamepad and your controller and your camera and your microphone. And what makes Windows really more complicated than most operating systems is the variety of devices that just seamlessly plug into it. I mean, even amongst your class, I bet you there's a very low probability that anyone is even running the same monitor. Has everyone got at least, like when you're running dual monitors, are both monitors the same make and model? They're identical. Yours are different. Right? So if you're working on art and you want red to look like red, does red look like the same red on both monitors? Not quite, right? Right? So there are tools to calibrate those things. Well, part of what makes Windows complex is that Windows can handle the fact that not everybody runs the same monitor. Not everybody runs the same microphone. Not everybody has the same headset. Not everybody has the same mouse. So all of those different devices have to work with each other, and the operating system has to balance that in between. And the way it does that is what we're interested in. Okay. The other things the operating system does is it manages interfacing with the user. So that's user interface control. And if you're familiar with working with a Linux machine, they manage that user interface radically differently. They separate out the operating system from the user interface. X Windows takes care of managing the graphics on the screen. The Linux operating system manages processes running in memory. And the two of those are independent. In Windows, they're glued together. You cannot separate them. Right? And the reason I bring Linux up is because it's an older, much more stable operating system. And the reason I don't bring Mac OS up is because Mac OS is Linux. All that Apple has done with their Linux installation is they've gone, it only runs on Macs, which is a smaller subset of hardware. So let's take away all the variability of all the different device types and only support the Mac devices. That gives them a much more stable operating system. So that operating system having to handle all of these resources is really the reason that your Windows machine doesn't feel as stable sometimes as some of the other operating systems. It also has to deal with anything that breaks. When was the last time something broke on your computer, some application froze and stopped, but you had to reboot the computer to get it back?
I blue screen the other day.
You see, that's very rare these days. What'd you do to make it happen? Can you reproduce it?
I think I was just booting it up and it just blue screened on me.
That's a troubling sign. That means something is about to go bad. Yeah. And if it's related to hardware, that's even worse. Right. I mean, the rule of thumb we used to have was that you would have to reboot a Windows machine every week. The combination of applications closing and crashing and the number of things you open and close would fragment memory so much it would just dissolve into poor performance, and by rebooting every week you wipe everything clean. Linux machines, on the other hand, typically reboot every 6 months. Okay. So that stability comes from having to deal with fewer different combinations and permutations of different peripherals and hardware plugged in. Failing gracefully from errors is also key for developers. Now, in most of the programming that you do this term and next term, you're not going to run into the failing ugly with a couple exceptions. But when something fails in any of the applications you're going to write in the next 6 months, largely that process or that application is going to fail and nothing else. So you're going to be able to kill that application. And you do that through the task manager. You go to your start menu and you bring up the task manager. Just pull it down here for a sec.
Or Control-Delete?
Yes and no. Control-Alt-Delete, you can get to the task manager. That's an old holdover from when machines weren't quite so stable. So this guy that we brought up before gives you an idea of all the applications or programs running. You typically don't want to play around with the background processes. Those things running in the background may be used by multiple different applications, so terminating one of those is going to be potentially hazardous to multiple things. But if, my source tree is being unhappy, I can come here and end that task. And that will kill it. So we can use some of the tools in the operating system to manage some of those resources. The resources we can play with, that processor, the memory, well, we can't do too much with the processor. And the operating system kind of hides that from us. It says, look, I got this guy. So you want to write your programs as if they're the only thing running on the machine. And you want to write your programs so that the operating system can take your program, locate it somewhere in memory, fake out your program so your program believes it starts at memory address 0, just like that little assembly language program, and you're the only person in control. What the operating system is really going to do is it's going to put you in your own private little sandbox to play in. And every so often, it's going to interrupt you and give control to another one of the programs on your machine. And that's where we're going to start talking about some of the task switching we're going to do. It's going to do that by consuming some memory. Now, eventually, it's going to run out of memory once you get enough things running. And so it's going to start to consume your hard drive. So it'll have a file on your hard drive. If you show all the hidden files and you look at the root of your C drive, you'll see a file called page file. That is the virtual memory. And typically, you want that to be at least the same size as your physical RAM. So whenever you run out of physical RAM, the operating system takes a program that's not running and it copies it onto the hard drive in that file. And when it's time for it to run again, it pulls it out of that file, puts it back into RAM, and sets it loose running again. And it runs for a little bit of time, and then it gets kicked out again. Of course, the operating system's constantly listening to those device drivers and those interrupts. And at the same time, it's giving instructions to the I/O controller. The I/O controller has been asked for various different reasons to retrieve information, which it buffers and caches in its own memory. And through an interrupt system, it can be told, go fetch some data, or I have data ready for a program to use. And the operating system has to take care of managing multiple requests to that piece of hardware from multiple different programs and make sure that the right data gets routed back to the right program. As far as each program is concerned, we want to create an environment where you, the programmer, feel like you control everything on the machine. You're like the only one there. It makes it easier to write software. Applications need to be built in a way that doesn't try and block that hardware. And more, it's really, really difficult these days to do so. Now, the one exception to this, and we'll see when we play with memory a bit, will be when we're playing with C++ applications. And the challenge with C++ applications is because you have more direct control over the memory space yourself, you can also do bad things with the memory space. And then bad things happen, and then it kind of cascades out of control, and you may actually have to reboot the computer. So, some of the things that most of our operating systems provide as additional tools to help us run applications really have to do with running things standalone. So running simple batch or configuration script type things. Lists of tasks, lists of commands in the operating system that we can execute a program, collect its output, do some extra work, and run that in the background without being interactive. In the game dev world, this fills in nicely, and we're going to tie into this in term 3 or term 4 when we talk pipelines. When we actually build automated build systems. You know, the idea here is to have the computer have the set of instructions to construct your game all on its own and make sure that it does it frequently and repetitively the exact same way every time. Consistency. So we're going to want to use the operating system's scripting tools to help do that manually or automatically. We're going to want to tie into the operating system's scheduling abilities to say, hey, every 5 hours, I want you to build a new build. And we're going to look at some of the tools that the operating system provides so that we can go, oh, and by the way, when I built that thing, which I do 4 times a day, I captured all the output and I filtered the output for all the errors, and I sent you an email with a list of all the errors in that latest build so that you know what state your game is constantly. Our operating system typically has to deal these days with our multiprocessors. Our Core i5, i7, i9s all have multiple cores. They can run multiple programs simultaneously. Most of our programs only consume 1 core at a time. Unless we do some really special programming, we're going to want to stick to 1 core. So our operating system has the ability to say, yeah, this program, that core, this program, that core, this program, that core. Now, fortunately, we don't have to write that operating system because that's a whole different story. There's other different aspects that we're going to have to deal with. We're going to have to deal with distributed computing. So where we do some of the processing on a different machine than the one we're currently on. We have to deal with some of the networking constraints that we have. And when we talk about cloud systems, which we're going to get to build by the end of term 4, those cloud systems are really somebody else's processor somewhere else on the internet, and it's hidden from us. We don't know who, we don't know where, and honestly, we don't care. I just want to do some work out there, and I want that work to be reflected in some data that was generated that I can later access. There's a couple other variations on operating systems as well. There's real-time operating systems, which are typically used in industry. And maybe you guys can think of where do you think real-time operating systems would be most common for most people? What would be the modern place that you would find most real-time operating systems?
Sure. Um,
Real-time. Anyone have a car?
I was supposed to say like an elevator or something.
Not real-time.
Or is
Elevators are mostly mechanical.
I used to have a car.
Right? Cars have computers in them these days. Those computers are not large, sophisticated like your Windows machine. They're small microprocessors. Like there's one piece of code and one processor handling your anti-lock brakes. And you probably don't want that to fail. And you probably want that to react in real time. As events happen, the processor and the operating system running on it react to it, right? Modulating or pulsing the brakes. It detects lockup, uses that as an input, and then provides brake on, brake off at a really fast frequency. In fact, cars these days all have multiple computers in them, and there's a standard by which those computers talk to each other. It's a thing called CAN bus. And you can look up on the internet how to program microcontrollers for automobiles. Other things that a lot of programmers get involved with have nothing to do with consumer products, but commercial software. Like here in British Columbia, we have these things called sawmills. And I bet you the guy operating the giant 6-foot-tall circular saw cutting logs up probably wants to know that the real-time operating system will actually respond when he pushes that red stop button and stop that thing from spinning. Or that the MRI scanner that's going to scan your brain is actually controlled by a piece of real-time software. Unless it really scares you that someone like you programmed the controller that's handling the MRI scanner that's baking your brain. Because it's not just a guaranteed piece of hardware, it's a piece of software that somebody wrote. So those are real-time operating systems. And they typically have some very tight constraints on them. They usually don't have a large amount of memory or a large amount of processing power. And they do one task. And they do that one task very, very quickly. And then you run into your handhelds, right? Handhelds being your phones. Your phone is a pocket computer more than it's a phone these days. The fact that it uses the internet to communicate to different things just kind of identifies that it's more of a computer than a communications device. But the processors on those things are a completely different beast than what's in your PC. So they all run an operating system as well. And in fact, the Android phones, it's a derivative of Linux. Yeah. So all of those things have to be managed by your operating system, right? We're taking a little look. We're going to focus on the Windows side of things. The multiple processors, multiple cores, handled entirely by the operating system. What program goes onto what core? And it changes. So our modern operating systems have what we call preemptive multitasking going on. That means if there's 10 programs running, each program gets a little bit of time. And they just go in a round robin. So everyone gets a little bit of time. And once their time's up, the operating system preempts them, kicks them out, and starts the next program running. Now it does that for every core. So if you have 8 cores on your machine, you can potentially run a lot of programs simultaneously. Right? This is why we say for a gaming machine, having more cores doesn't necessarily make your game faster. Having a Core i9 doesn't run faster than a Core i7 when you're playing games, because the game software that the programmers wrote doesn't take advantage of those multiple processors. You can get maybe a couple going if you start using coroutines in Unity and C#. If you fork processes in C++, you'll consume a couple of those cores. But for the largest part, it's just one. In fact, you're going to go faster if you get a higher clock rate processor than a higher number of cores. The biggest thing that makes your computer go faster is memory. If you don't have to use virtual memory, virtual RAM, and by virtual RAM, I mean when you run out of RAM, it uses the hard drive. And the hard drive is about 1,000 times slower than RAM. So if you have to take the entire contents of Unity and swap it out to your hard drive 30 times a second, that's going to slow you down. Having more RAM, you don't have to swap to the hard drive. You don't have to swap to the hard drive, things go faster. That's the nuts and bolts. Okay. Key things, well, the user interface is fairly obvious and constantly changing, sometimes just because we get bored with it. Both Apple and Microsoft have usability labs that are fairly extensive, that they try and test and try out the usability of the windowing environment that they've provided to people to try and make people more productive. And we learn a few things from these, and you will in the UX course. There's an entire branch of engineering called human factors engineering about how human-machine interfaces work. And some of the things we will percolate into some of the applications we make. Things like people don't really read labels. People remember positionally where UI elements are on the screen. Right? That goes true for games as well. You remember where the UI elements are on the screen when you have to click them with a mouse. You get to learn where HUD elements are on the screen and you look for them there. And if they're not in the normal place, it takes work to go find them again. It also means when we're building apps, we don't really want to change things around in our user interfaces too much. Once we get a user base used to the way things are laid out in our app or our game, changing them will really mess up those guys. So all about the user interface stuff and the way the different operating systems manage that user interface. Now, the biggest thing it does in the background, though, is that preemptive multitasking, right? If you saw my task manager, I got a lot of Chrome stuff running. I got OBS running. I got Discord running. I got some web stuff running. I got some editors running. I got source tree running. All of those applications are consuming some of my CPU. So let's take a look again, and we'll see if we can't blow this up. Huge. And get an idea. So by exposing mine, you start to see some of the things that are going on. First of all, you can always sort by these columns by just clicking on them. I can see that I'm using a whopping 18% of my CPU, and that my machine's just running on a Core i7. So I'm not really taxing the CPU at all. I am using 64% of my memory, and given that I've got 32 gig on this machine, look at that, my voice is going. That's a pretty reasonable amount, and you'll also see in dark orange here, surprise, surprise, the 97 Chrome tabs are kind of, yeah, that's right, you're reading that right there, 97 Chrome tabs open. So Now, the real party trick here is when a friend of yours who doesn't know this says, hey, my computer's running really slow, and you bring up the task manager right away and see 97 Chrome tabs, you'd be like, well, maybe you should close some tabs. And you get some memory back, and you won't be like hard swapping to your hard drive. You can see my disk is at 0% and my network's at 0%. Now the disk makes sense. I have enough memory, I'm not touching the disk. Why the hell is the network at 0%? I'm streaming. Why is the network at 0%? How heavy a load is streaming, do you think?
Very heavy.
Very heavy? It's not very heavy at all, actually. I mean, what am I taking here? I'm taking a 1920 by 1080 image, which is a meg, and uploading it 30 times a second. The rest happens on Discord servers, where it distributes it to you guys. Plus, I've got all of your streams coming down, but they're all thumbnailed, so the server's squishing them for me. So I'm not getting the full size feed. And I've got a relatively fat internet pipe, so the combination of those things gives me reasonable network bandwidth. You'll also see my GPU grinding away there. And the GPU running about 20-30%. One, I've got a lot of programs running. Two, it's decoding all the video streams. And three, it's encoding the stream headed up to YouTube. So it's doing a little bit of load. And again, we can look at the performance side of things and take a look. I can look at the logical processors. Adding more processors here by going to a Core i9 doesn't make me any faster because most of them are just idling anyways. The CPU speed, 4 gigahertz, that's what makes me faster. A Core i5 running 5 gigahertz is going to play a game faster. Memory, we can see we're kind of creeping up there. Disk is nothing. My second disk is nothing. The internet's sending some stuff through. This is scaled. But really, on the grand scheme of things, what am I uploading? 3 megabits? It's not that huge. And my GPU is mostly doing video encoding. And because it has enough video RAM on board, it doesn't even have to touch main RAM to do so. So what we're going to focus on today is our processes here. All of these processes are running simultaneously, and the way they're running simultaneously is the operating system loads them all into memory, and then it gives each one of them a time slice. And as each one of them operates for a little period of time, it gets interrupted, and the next one gets to go.
So it's like a line. It goes through a line.
Yeah. All of these background processes get a time slice as well. Right? And you can see there's lots of them. And you can bring this up for your own computer as well. And then the Windows processes. And they all get a time slice. And there's just a few. So you can flip through and see what's really going on your computer. When we look at older computers, it's easier to see because they don't have as many cores and as many things running, and it's slowed down and you can see what's going on, but the principle is the same. So that task switching, that's really what our operating system is focusing on doing. Now, because these things let us run multiple things side by side, we get an idea that our program isn't the only thing in the computer. And so our program needs to compensate for that. And the weird thing comes about is when you're building a game, how fast do you want your game to run? What speed do you normally think of games running at?
60 frames per second.
And why do we run at 60 frames a second?
That's the next question. Like, is the optimal one, like, not too heavy, not too fast, something like that?
So
I'm sorry, Scott.
Like under 25 FPS, we will see the lag in our eyes. We can see that, so it must be over 30, but actually 60 is like above, like in the middle of low quality and high quality, so it doesn't use so much frames to run through it, I think. Oh.
No.
There's something about being divisible by 30 as well.
It kind of goes in steps. Part of it is historical. Part of it has to do with physiology. Film runs at 24 frames a second. Movies. Do you notice blur and lag in a movie?
Nope.
No.
But it's only running 24 frames a second. 24.97 to be precise, but why do games run at 60?
Because it is needed, but the minimum.
Oh, we used to run games at 20 frames a second. So the historical part has to do with screens and displays and monitors, which we're going to talk about in more depth. But long story short, before LCD panels, we had cathode ray tubes, tube televisions. And the way cathode ray tubes work is there's an electron gun at the back that shoots at the screen, and two sets of magnets, one above and below, one on each side. And the electronic controls put different power on the magnets to make that electron gun sweep out the whole screen. And it takes a certain amount of time to sweep from left to right, top to bottom. That's the historical part. So what they did for television and CRT signals was they defined a timing that gave the electron gun enough time to sweep out an image. And that's where the 15 frames a second, 20 frames a second, 30 frames a second kind of comes from. And that was to give the screens enough time to sweep it out. Now, a modern LCD screen doesn't work that way. Your modern LCD screen, regardless of the technology behind it, for the most part, is a bright white bulb behind a mask. And the mask has a bunch of really, really tiny little flat doors. And the doors can be partially open or fully open. And so if you stack up a red, a green, and a blue door in 3 layers, and every pixel has one of those doors, you turn the red off by opening it all the way, you turn the green off by opening it all the way, and you leave the blue closed, you get a blue dot. And once it's in that state, it stays in that state until it's changed. That enables our modern LCD monitors to technically go faster. The speed, the frame rate, the refresh rate, you talk about 120 hertz monitors, 144 hertz monitors. It's the speed at which the electronics in the monitor can flip every pixel. How quickly. And when they talk about hertz, they're talking about cycles per second. Okay. The reason we go up to 60 frames a second has to do with the fact that your hands are slightly more sensitive than your eyes. So while your eyes can be deceived by 24 frames per second, which the next step up for those CRTs was 30 frames a second, your hands can tell the difference. It's like motion sickness. your hand moves something, you expect to see the result right away. But what you know about operating system now, your hand moves something like a controller that triggers an event or an interrupt to the computer. The computer has to handle that interrupt, tell the right program that something happened. That program has to react to that, change something, and then redraw the scene. So the change, the reaction, the redraw the screen, that means what you do on the controller is often 2 or 3 frames behind you actually doing it. So you get this weird feeling when you're playing a game at 20 or 30 frames a second, like, I moved the controller, damn it, how come that didn't move on the screen? Right? Because your eye tells you that it hasn't happened yet, but your hand is saying, oh yeah, it did. So that timing lag is why we push for faster frame rates. And 60 frames a second, the next step up. And they're discrete steps. So from 60, you go up to 120. And the 144 is weird. I have no idea why someone decided 144 was a good frame rate. 120 makes the most sense because if you're doing 2 screens and you had to draw 2 images, you would want them both running at 60 frames a second, which means you effectively have to do both screens, different views from different cameras. Where would that come in play? Where would you watch 2 screens from 2 different cameras at the same time?
Studio office? You watch 2 pieces of it? No?
I dive out of the view for a second. And I show up with... All virtual reality really is 2 cameras placed camera eye width apart, rendering 2 different copies of the same scene from slightly different camera positions. And your brain puts them together. But it does accentuate that frame rate problem, because now if both eyes aren't in sync with each other, you really messed up. You might as well be on a ship moving at sea in 4-foot seas. Right? So that parallax between your 2 eyes is what makes virtual reality feel 3D. And what we've learned is that it's very nauseating unless your frame rate is running fast enough. So we typically want that running at a 60 frame per second minimum times the 2 different scenes. So you need more memory, 2 screens, 120 hertz, 120 frames per second. Right? So how do we get all of that frame rate when our stupid operating system keeps taking our program when we least expect it out of memory, throwing it on the hard drive so the background clock application in Windows can run? And that's what we're going to kind of wrap our heads around so that we know what that task switch is all about. Okay. Now, here's where we tie in that assembly language stuff. When you did that little assembly language routine for me, what you may have noticed is that there was a register called the instruction pointer, and that pointed to a little chunk of the memory. And every time you did an instruction, it moved to the next kind of instruction. And this is exactly the way your program works. When you build a program on your computer and it compiles it into a machine language, the machine language gets loaded into the CPU or into memory where it gets loaded to the CPU, and the CPU walks that instruction pointer through your program. As it gets to each instruction, it executes it. When it's time to interrupt your program, your operating system then needs to save the current state of everything. So before it can swap your program out, it needs to figure out where was the instruction pointer, what was the status of all the registers in the CPU, all the flags, and save that context, as well as all of the memory attached to your program. Takes that, puts it in a chunk of memory off to the side. If it doesn't have enough memory, it writes it to the hard drive. And then it takes that exact kind of information for the next program to run. It loads it up, resets the instruction pointer, lets that program run for a while. So these are our ways of doing the instructions. Now, that the way I usually illustrate this is we often will play a little game. And the problem is that the game requires like a musical chairs thing, 6 seats, and 12 people. Now, I don't know about you, but I see a slight image or slight problem with trying to get 12 people to occupy 6 seats in this particular class. So we can give you the idea. I usually use a checkers game to illustrate this, but we play checkers as if you were building it for the computer. So we take a look at how would we operate a checkers game. And forget about the numbers in here in terms of the seats. We do this in person, right? You can only do one thing at a time. And doing those one thing at a time, you need a set of instructions. And so one person takes the role of being the instruction pointer, of telling everybody else what to do. And everybody else gets to do one task. So somebody gets to do the reset the board. Somebody gets to move a red unit. Someone gets to move a black unit. Someone gets to update the score. How many have each team lost? Someone gets to crown queens, and someone gets to determine the winner. That's at least 7 different tasks. Trying to do it online, I can use my fancy checkers game. What do you think we're building in the HTML game? Oh, no, we're not going to build this one. It's okay. No, this is too easy. This is too easy for you guys. We're going to do something more. Something with more meat to it. Right? But, or maybe we... spelt it wrong, didn't I? You see my typing skills are top notch. Raphael.
Oh, whatever. Not too nice because I like the game, so.
We're going to cut David out for a while. Right? So when we look at kind of reset the board to start, we've got that, move red. Well, the only people that can do things are the people in the red boxes here. So, move black, move red. Arsenic, move red. Should be move white. So we can grab a piece, maybe, and move it, right? And then move black. We move it. And we go back to our instructions. Move red, move black, update red, black score. Update score. So Jim would then come along and update the score. There's no score to be updated. So the next thing we would do, crown any queens. In order to crown the queens, we need to figure out, are we going to have any queens, which means somebody has to move that task into memory and some task has to go out of memory. So this is what your operating system is doing when it operates your program. Hopefully you're never moving things from memory to your hard drive. Hopefully you're just moving things in and out of memory. And then when it's time to interrupt this program, you have to take this whole state of things and save it somewhere. Now, I guarantee you that watching my checkers board behind me is nowhere near as fun, so I'm not going to walk through playing the whole game here. As it is when I lay out the big cloth map on the table at the back of the room in the school, and you guys get to play checkers, but you get to play checkers where you can only do one thing at a time until somebody puts you in the right chair. Right. Which generally creates a little bit of confusion, but you get the idea of the kind of things that your operating system is doing behind the scenes for you. And as you write applications, you're going to write your application like you're the only thing on the computer. But at the same time, you need to be aware that from time to time, you're going to get interrupted. You're going to have that little hiccup. And you've all seen this when you have tons of stuff running on your computer and you go play a game. Right? And in the middle of the game, there's these little hiccups from time to time. And you think, oh, it's the network stuff. Oh, it's something I'm doing in the game. Oh, the game's just buggy. And what it could very much be is just that you have so much stuff running in the background while you're playing your game that the operating system is just giving the other things a time slice to run while your game plays. Which is also why, and I'm sure you've all done this, you're playing a game on your Windows PC and it's got a few of these hiccups going. And so you pause the game and you go back to Windows and you close a bunch of things, right? Because you're freeing up memory and you're freeing up some of the tasks that Windows has to do. For me, I close Chrome. That's like 97% of my memory comes back to me. Right. Right. There's a couple other things you got to do as well. In Chrome, you probably want to, we'll do this on Friday, but some of the settings that you want to set in Chrome with a modern fast computer is you don't want Chrome to stay in memory resident when you shut Chrome, which it has the option of doing by default. And you want to turn that off because your computer is fast enough that it doesn't need the performance boost for restarting Chrome by having Chrome sit in memory in the background. Okay, I'll show you what I mean. So that's kind of the checkers game I usually use to illustrate that task switch stuff and how much the processor has to flip tasks around. I'm going to kind of stop there. We're going to take a little break. You guys should get up out of your chairs and stretch a little bit, take a bathroom break. I'll come back 10 after, and we'll start talking about some of the other things RAM related that your operating system does and try and get an idea of what can we manipulate and what can we not manipulate. It's all kind of theoretical stuff, but hopefully as you start writing applications, some of this stuff in the back of your head will help you go, oh, if I do that, this bad thing might happen. Or if I do this, that'll be better for my application. Right? All right. So I'll come back 10 after. Okay, guys, let's get into a little bit of what's going to work with some of your applications. So the first thing I talked about was memory and how are we going to manage memory. So the best way to think about the way your memory is laid out is to actually look at our memory as a giant strip chart. And to always think of that strip chart in terms of how your application fits together. Now, on the left is the way your computer is kind of laid out, and on the right is the way your application fits into it. Now, our Windows computers still have this weird architecture because they're trying to emulate what original MS-DOS machines could do. You know, the machines that would never need more than 640K of RAM ever. And that was one of the restrictions that was built into the original Windows, or the original MS-DOS operating system that Bill Gates put together that started Microsoft. And it's not until very recently with Windows 7 that this memory area has been virtualized. In other words, the operating system takes care of recognizing here's an application that's running in compatibility mode. If you right click on the File Explorer on any application that you're going to run, I'll see if I can bring one up here. Let's just go look at something simple and straightforward. If I look at this application and I go to Properties, and let me just bring that up here. If I go and look at my application properties, I can go into compatibility mode. And compatibility mode lets you change not just the DPI settings, but run this program as if it's running under a previous version. Now, these are all virtualizations. And what they're really doing is they're telling our operating system that we're going to treat your application as if it was running in a previous version of the operating system. That's kind of what we see in the right-hand chart. The left-hand chart is the real version of memory, where your application could be located anywhere in memory at any time, and you don't know. The operating system manages it. That means in your program, while you're writing software, if you allocate a variable, those variables get allocated at a certain memory address. That's what the compiler does behind the scenes for you. Those memory addresses are relative to memory address 0. That makes the compilers work a little bit easier. The operating system remaps that every time it switches your program in memory. So it manages it for you so you don't have to. This means, once again, that we kind of write our programs as if we're the only thing on the machine. When you're inside your own little space, you have all of your data loaded in front of you. And the way you occupy memory is kind of the way this diagram shows things. If you flip it around, think about that assembly language program. The data was at the top. That was defined first. So that was the stuff. Here, memory address 0 is at the bottom and it's going up. I often draw these the other way around. So at memory address 0, we load some text, some data. And then we load our code. And then we have what's called the heap and the stack. So the heap is where we allocate variables in memory. When you're in your programming language and you declare a variable, whether you're using a strongly typed or a weakly typed language, the variables you declare get carved out of the heap. they grow up. As you make function calls or method calls, you take all the parameters you're going to call and you push them on the stack. And the stack grows from maximum memory down. You push those variables on the stack, you make a function call. The function can then pull the things off the stack. And when it returns a value, it returns it by pushing it onto the stack and then returning execution back to your code, wherever it left off. That jump to the subroutine and return back to where the subroutine came from. We use that stack to hold temporary things. Okay. Now, occasionally, very, very infrequently, but occasionally the heap and the stack will collide. So you'll add stuff to the heap and add stuff to the heap and add stuff to the heap by creating more and more data or variables at runtime to the point where it may actually run into the stack. Okay. Now, if that happens, it can only happen in C++. If it happens, you're going to have to find a way to, as you're allocating stuff, not allocate it all in memory all at once. And there are techniques for doing that. The likelihood of you running into that is very, very low. Does anyone have an idea why languages like JavaScript and C# and Python don't have that heap stack collision?
The system decides for you.
That's part of it. Yes, that's why. They have part of the operating system that they engage is a garbage collection system. And the way those things work is always the same. When you allocate memory, it allocates memory the same way on the heap. It takes a reference to it and it stores it inside the operating system. It keeps account of how many references to that chunk of memory exist. In a garbage collection system, if that reference count ever drops to 1, that means the operating system is the only thing that still has a reference to that memory. It means nobody's using it, because if the operating system is the only thing that has a reference to it, nobody else does. So periodically, one of those context switches, one of those task switches, it can run its garbage collection process. And the garbage collection process goes through all the references that have only one use of a chunk of memory, and they free them up again. So that your heap never really grows to the size of the stack because it's constantly being cleaned out. People usually claim that those kinds of languages with garbage collection systems are much, much slower than non-garbage collected languages. Over the last decade or so, we've kind of proved that the machines are fast enough that that context switch and memory cleanup happens so quickly that it's a negligible performance hit, and most people can just safely ignore it. So know what's going on in the background. Know that in C# and JavaScript and Python and pretty much all interpreted languages, there's a garbage collection system. And that the only exception to this these days really is your C++ programming, where you're responsible for deleting and cleaning things up behind you. So if you allocate some memory for a variable, you need to make sure as a programmer that you deallocate that memory at the appropriate time. Right? And that's easier done if you're doing it through methods and functions, because those variables end up being on the stack and the stack automatically cleans itself up when you return from the stack. But if you're storing stuff as part of your application's memory space, you need to be aware of how much stuff I got and where is it. Now, how do we manipulate this within our application? Well, like I said, we declare variables. We store information in variables. There's no special magic behind it. And we do assume that everything starts at 0 and that we're going to go through and allocate things as we need them. The language that we're using to do our programming in will help us dictate how much space to allocate for every variable that we have. To be clear, even loosely typed languages have to know how much space to allocate. So when you allocate a number in JavaScript, which we're going to do very shortly, that number is going to get stored somewhere. The difference between something like C# or C++ that's compiled and JavaScript or Python is when that space gets allocated. In C#, it gets allocated the moment the program runs, because you tell it, oh, this is an integer, so I need to allocate something the size of an integer to put that variable in. In a loosely typed language like JavaScript or Python, you get a reference, and it's not until you actually assign something to it that it goes, oh, the thing you assigned to it was an integer, so let me allocate the size of an integer, put your number in it, and then attach your reference to it. Does that make kind of... Right. So we use variables to allocate memory and to manage memory in our programs. And variables need two things to them. They need a type and a scope. Type is how big is it? What kind of thing is it? And scope is visibility. Where do I allocate and deallocate this thing? Okay, so global scope, bad only because they all got to have some unique name, which means you're going to run out of names, which means the names are going to get ugly. And somebody's going to overwrite it without knowing about it because they didn't use it the right way. And you'll hear all sorts of preaching about that. Or block level scoped, right? You're writing some software and there's some curly brackets that define some block, and so you allocate a variable inside that block. When that block exits, that variable goes away. If you're in C#, the garbage collector cleans it up. If you're in C++, you have to delete the memory before you exit. It's up to you. That means that how they're managed really depends on how your programs are built. And there's kind of two flavors of this as I list here: compiled languages and interpreted languages. And both of them operate on a similar principle. Generally speaking, people think of interpreted languages as slow, although again, our computers are so fast these days that slow is kind of relative. The compiled languages are the languages that we typically think of as those third level languages. That's our C#, our Java, our C++, and there's a bunch of other languages that we're going to play around with you guys, probably in the next class where we get to try out some different things. In addition, interpreted languages run a little bit differently. They don't walk through the entire source code and generate some intermediate object code that gets linked together with all the other object code and run through an assembler where it generates machine code. Interpreted languages, your source code gets taken one line at a time. It gets compiled into an intermediate code and interpreted instantly by being turned into machine code, which gets run right away on some sort of virtual instance or machine. When we're working with the web, that virtual machine is Node.js. When we're working in Python, it's the Python runtime. When we're working with Java, it's a hybrid between the two. Java's compiled, but there is a Java virtual machine. C#, C++, they get compiled directly into native Windows, Microsoft, Intel Core i7, Core i5, Core i9 machine language. So those effects really kind of came out of two different schools of thought when these languages were built. And all of this has to do with how do we manipulate memory in our operating system. Within our program, we're allocating variables. The type and scoping parts are different depending on which language we're using. So we're going to focus on the compiled part for the first part because that's largely where our game code lives, right? So compiled languages kind of all follow this basic process. We're going to create a high-level English-like language that is probably going to feel really challenging if you haven't done any before. For you guys, I'm assuming this is going to be pretty straightforward to begin with. These languages are designed to be expressive enough for you to solve problems with, and yet concise enough that they're unambiguous. And that's key for the computer. Things have to be unambiguous. You can't have multiple meanings, for one thing. All of these languages follow the same process. You write some source code in multiple files. You use a tool, a compiler, to generate an intermediate format that can be linked together. And the linking process is about resolving symbol names, making sure that a symbol name in one file matches up with the corresponding symbol in another file. If you use a variable and you give it a name, you have to be able to find that variable in another file you're using. You need to be able to cross-link those namespaces. So the linker resolves all that and generates some assembly language. And that's what you were writing the other day, the assembly language part, which then goes through an assembler and generates the appropriate machine code. And as you can imagine, a couple of these pieces are, always the same. So the modern Microsoft compilers, for instance, are a compiler, linker, assembler, all in the same program. So somebody used the tool chain you see here to build a program. Generally, they're written in C, and those programs are compiler, linker, assemblers. If you go onto your Windows machine and you have Visual Studio installed, if you go and try and find cl.exe, that is the compiler linker for Microsoft's toolchain. Okay. And there's a C# compiler linker, different program. If you're on a Linux machine, it'll be GCC for the GNU C compiler that gets put together. So all of those are separate programs that take source code in, do the compile, link, assemble process, and spit out native machine code. The way that the compiler, linker, assembler are put together in those programs is that they use command line options. So if you're using your terminal and you were to try and do it manually, they use the command line options to give you a folder for what to include and what to link together. And you can also run them independently with specific command line options. But for the most part, they want them to operate kind of smoothly. Now, interpreted languages, on the other hand, need some sort of environment to run in. And the interpreter reads a line of source code and passes it to the environment. And the environment does the compile, link, machine code run for one line at a time. There's good advantages to this in some cases, and there's a lot of disadvantages in some cases. The biggest advantage is it's faster. It's faster to develop. You can imagine a large game application that takes 3, 5, maybe 15 minutes to compile. It means every time you change the slightest little thing, you've got to wait another 15 minutes to test it. Interpreted language get away from that by doing things one line at a time. They do have drawbacks. Sometimes they're slower. Mostly the biggest drawbacks have to do with scoping, in that a variable has to be in some way used before, or can be used before it's actually been defined, which means it's going to break. You're going to try and access some memory location to get a variable, but that variable hasn't been declared or defined yet. And the program will break at runtime right away, and you won't really know why. So they're a little bit harder to build and debug. on one respect, and they're a little bit faster to build and debug on another. It's quite a religious war, if you really get into it, between whether interpreted or compiled languages are better or worse. So I think you're just best to stay away from it and recognize that they each have purposes, and they each have strengths, and they each have weaknesses. Python has become the darling child language for machine learning and artificial intelligence. And there's very specific language reasons why that is, right? Lisp, almost nobody knows what it even is anymore, but there's generally more parentheses than actual textual words in Lisp, so it's kind of hard to read. It's very powerful for processing lists. JavaScript has become the language of the web. Anything that you want to do distributed on the web, client or server side, probably you're going to write JavaScript. And JavaScript, because of that, is probably the most widely known language. More developers out in the world, because there's so many web applications and websites that rely on it. The process that follows looks kind of like this, right? You start your text editor and you just edit away, and it generates, the interpreter generates the executable bytecode for one line as it happens. The compiler gives you the ability to have a tool show you all of the possible problems and things it's going to have before you begin. So when you're learning, it's a little easier to have the compiler point out all of your mistakes, specifically syntax mistakes as opposed to semantics. So where you put the commas and the semicolons and the curly brackets, if those aren't right, the compiler doesn't make it all the way through, and it'll tell you. The interpreter, if the first 3 lines are right and the 4th line is wrong, it won't tell you till you get to the 4th line while your thing is running. Okay. Now, the way things refer to memory also varies in these different languages. So if I follow my little diagrams here, I think it might be easier. Now I'll just do that. So when you're creating data, what you actually kind of do is think of memory as a giant strip chart. And when you allocate some memory, you're going to declare the kind or the size of it and how visible it is. Is it visible in this block? Is it visible in this function? Is it visible in this object? Is it visible in this method? What's the visibility? And those things have various ways to be defined. In the examples I have here, they're almost all C++, because when we look at how our memory is referred to, we're going to have to get into the difference between the memory itself that we're allocating and how we refer to it. And how we refer to it is with a reference. And there's different ways that we indicate that in different languages. So you see in the top part, I've got my declaration part there. That int of var equals 3 is the way C and C++ declare variables. The next line down, integer of var equals 3, is the way C# and Java declare variables. And to be clear, if you haven't kind of clued into this, Java as a language built by Oracle and Sun Microsystems, and then when Oracle bought Sun, they took over Java, and Java was seen as the replacement for COBOL for business applications. And Microsoft says, well, we can't have that. It's not built by Microsoft. So they said, well, how can we improve on Java and make it our own? And so they built C#. And C# has become the language of choice for Microsoft applications, but it's only on Windows machines and only by Microsoft. Whereas Java is operating system independent. Now, in one of these languages, C and C++, you can modify all parts of the memory you're allocating. And I'm going to drop down to my little drawing pad to give you an idea how this kind of works. So the same as I had in the slide there, if you think of memory as this little strip chart, and you were to start at memory address 0, and now you allocate an integer. So I'm going to carve that off, and I'm going to put my integer in there. I'm going to refer to it by something, so a variable. Okay. Now, this guy is a reference to this chunk of memory. In one language and one language only, can you change this, this, and this reference? And that's C++. In all other languages, you're not allowed to change these two things. What I mean by that is, let's say I create another variable. I can take this variable and change what it refers to be this guy. I no longer have access to this chunk of memory. I don't have anything pointing to it or referring to it. This is referred to as a memory leak because there's no way to deallocate the number 13 and the memory that it consumes. Okay? So in C and C++, you will have to learn the different techniques on how to deallocate memory as you go. Modern C++ has the notion of what we call smart pointers that will help with this tremendously. Traditionally, if you allocate some memory, you have to also deallocate it when you leave. Now, in C# and in all of the interpreted languages, you can't mess with what the variable refers to. So you can't make this mistake. Back up a little.
Another question.
Yep.
So I'm seeing that the C++ has all these benefits, but the problem that you can have memory leaks and these other stuff. What are the benefits for having all those risks?
Well, you can do a lot of things a lot faster and easier. So, for instance, if I'm doing a thing where I'm walking through a list of data structures that represent characters on the screen, let's say I've got characters, right? In C#, I might have to have a list of characters. Or I might have to have a character array to contain all of the items in the list. Okay. In C++, I just need a pointer. Because when I tell the pointer to go to the next item, it goes to the next item. Now, a list of characters is a big data structure, so that consumes memory as well. And inside there, it's got a reference to each thing. Right? The character array also consumes some memory and has a reference to each thing. It's just a different way to represent it. The character pointer is the same size as an integer. So it's way smaller. Now, smart, sophisticated guys will do really interesting things. Get rid of this guy. Oh, I've run out of stuff. Get my little eraser going. So one of the things I can take advantage of here is if I'm allocating memory, one of the things I could do is keep just a couple pointers. So now memory, let's say I'm storing some data structure for my game that represents where every enemy is. So when I start allocating the next enemy, as I create a new enemy, I just allocate at memory current my new enemy. Smaller again. And then I move memory current pointer to the next chunk of memory. Enemy 2, move the pointer. Enemy 3. So it's a lot easier to walk through things and create new things.
So this one pointer doing all the job, not the structure doing it.
Right.
I think behind the scenes the same though. Like in C#, if you pass like the value of a, or you pass a list variable in like a function,
yeah,
it'll be passing a reference on the actual object though, wouldn't it?
Yes. So C# passes everything by reference for efficiency. Right? So you can still modify the contents of things, although you're not really going to want to do that. The difference really comes is when you start doing things like if I want to make a copy of it or I want to count how many things are in it. A lot of times in C#, it will actually duplicate the thing in order to count it or to walk the list of it, and then delete the duplicate after it's done behind the scenes. And definitely some of the interpreted languages do that. You know, if you make a list longer by one element, in C++, you just move the pointer. In C#, you want to make an array one element longer, you have to make a new array that's one element longer and then copy the old array into the new array. So that's why the C++ advantages kind of outweigh the pain. Right? So those are some interesting ways. The thing I typically try and get people to do, and let's see if I can delete a bunch of this. Just start over with my little drawing tablet. I had to go find a one button delete all. So one of the things that we find, I just go top down. So if I go 0, go that way. So if I declare a variable, I can grab the address of it. That's where does it exist. The variable itself is that number. And we can also grab a pointer to it, or the contents of it. So there's some ways that we use to refer to these things, right? We've got our variable, we've got the address of our variable, we've got the contents of our variable. The address of our variable, if I change the address of the variable, I might have change it to this guy, and it leaves a variable floating around. If I change the contents, I'm just changing this value here. But not the address. And C++ is the only one that lets you manipulate all three things separately. Yeah. So sometimes you can do that to advantage. Sometimes the confusion it creates is not advantageous. Right. Now, if we flip over to interpreted languages, things are a little bit weirder. So using that same kind of model in an interpreted language, what we really have is everything's a reference. So when we start looking at allocating memory, we don't know how much we're allocating until we actually use it for the first time. So we think of it slightly differently. We declare the variable name as a variable itself that's a pointer type or a reference type. And we can assign it to something at runtime. And at runtime, we figure out how big to allocate it, and we connect the two up with a pointer. And we can't refer to the pointer directly, but we can change the contents of it. So if I were to do that same kind of idea on my little strip chart, let's pull that back here. And I were to go and look at allocating some memory here, I allocate a variable, and that's where it stops. Now at runtime, when I assign a value to that variable, then they get connected. And the language knows that when you refer to a variable to retrieve the contents here. When I decide to change it and make a variable equal a string now, all it does is it changes this guy. And this gets disconnected. And that leaves that 13 hanging around in memory, right? Which would be a memory leak, except we got a garbage collector. And the garbage collector collects that up. Make sense? Okay. If it doesn't make sense, don't worry about it, because when we come back to doing this in the various different programming classes, I'm hoping that having this kind of mental picture in your head will help you go, oh, that's what's going on in the background. So I threw this in there for these kinds of reasons. When we talk about declaring variables, and this is very C++ specific, the way you read them kind of should fit together. So if I declare an integer size thing called a variable and set it to the value 3, that's just a normal variable declaration. It allocated an integer, put the value 3 in it, and a var refers to it. The way we read the next line, I have an integer pointer, that's a new variable the size of a pointer to an integer, called a reference, and that equals the address of a variable. So we're taking the address of the first thing and shoving it into a reference. Old school C would write the allocation this way. How's that for cryptic? So the integer pointer, variable 2, we're going to take and memory allocate the size of an integer and turn it into an integer pointer and assign it to variable 2, which is an integer pointer type. And you read the star in front of things as the contents of. So the contents of a variable 2 equals the contents of a reference. And then we would use free to free that memory up again.
The memory that it was allocated, right?
Right.
Okay.
Okay. That's doing the same operation that the garbage collector does. Okay. Now, what you're going to get shown how to do is how to use smart pointers. And smart pointers try and deallocate memory for you by declaring them a certain way when you declare them. So this declaration is not something you would do, this malloc, right? I'm using an memory allocation. It's C, not C++. Okay, but C++ is a superset of C. So the reason we wouldn't use that memory allocation is because it doesn't tie together with the free part nicely. You know, they can be in two separate places in your program. There's no way to link them together other than programmer discipline, which means people forget them. And so you end up with programs that have memory leaks. And those memory leaks never get cleaned up until the whole process is killed by the operating system. Or your machine blue screens and you have to give it a 3-finger salute. You got it. Now, strangely enough, there's some weird things you can play around with here. There's some more examples in the deck where it's talking about how to create a variable X and Y. Ways you'll see this written. It doesn't matter which side the star is on in C++. Integer space star P and integer star space P are the same. And you just read them as an integer pointer. So P points to the memory address of X. Okay. X and Y filled in. This is how IBM fills in memory, by the way. It's not with zeros. It's a hexadecimal number. But IBM fills it in because IBM's head office is in Texas. You don't get the reference?
So I'm creating a pointer and set a pointer to get a reference of X. That's right.
Right. So the pointer P contains the address of X. Right? Here's the address of X. There's X. It's at this memory address. The contents of P is what? Right? I've now set it to a value. P is the address of Y now. And now I've set the contents of P to 2. Right. So when we declare things, like I said, either way, again, I only go into this in C++ because it's the only language where you can manipulate these things directly. And there are times when many implementations can be made very much faster by implementing them using pointer arithmetic as opposed to creating duplicates and large data structures in memory. Now, the operating system manages all of that global memory and it manages the application memory. If in your modern preactive multitasking operating system something goes horribly bad, like for instance, where you had the contents of certain values that were your stats for your RPG character, and you started writing memory addresses in there instead, and the memory address was bigger than the size of the integer, then it would just overwrite the next thing in memory. Now, if you extrapolate that to, I'm using some more complicated data structure that represents all of the stats in my character, and I were to overwrite that with an address by making a mistake in my C++ code, the next time I read the data, it would just read the address as if it were the live data. And so you get addresses and data mixed up, and you don't really realize it until bad things happen down the road. So this is why we talk about C++ as being challenging to program in. It's also why if you kind of wrap your head around and master how you can manipulate memory directly with C++, almost all other languages become relatively easy to understand because they're simplifications of what's going on there. Okay. Your modern operating system won't let you touch memory outside of your little sandbox, your application sandbox. So you don't have to worry about overwriting the operating system or someone else's program or anything else along the way. The worst that will happen is that you will mess up memory in your application, and instead of writing in the heap, let's say you pick a memory address randomly in your code and you start writing your data into the middle of your code. The data that you write will just be interpreted as bytes. The program will start running those bytes, and if it doesn't recognize them, it will crash and probably lock up that process. So knowing how to kill that process is kind of key. And then the other thing that the operating system has to do is, as I said, it's swapping your program in and out of memory all the time, or in and out of portions of memory, or out to the hard drive. Eventually things are going to get fragmented. You're going to load something of one size and then load something right after it, and then the thing in the middle gets freed up. And the next thing to run doesn't fit in the hole, so it goes after, and then one of the other things gets freed up. And eventually you don't get enough contiguous memory to hold the next program. So the operating system manages that for you too. And it just tries to find a collection of holes that will fill. And it bridges the gaps between them and manages mapping the memory addresses between them. Because that fragmentation never really goes away unless you shut down all your applications, that's why as a developer, it's helpful to reboot your machine semi-periodically. I would say at least once a week. Now, I say that because out of habit, I can tell you I almost never shut my machines off. So rather than having the power supply go on and off and on and off and breaking, I let my machines run almost 24 hours a day. They might sleep or hibernate, that's fine. But I just tap a key on the keyboard and I'm back up and running. But at least once a week, I will shut everything down and reboot the computer because of this memory fragmentation part, so that it has a chance to clean up behind itself. There's a little bit more detail on how we do that, but that's kind of the nuts and bolts behind what our operating system does for us. And hopefully, the next class we'll get into actually playing around with allocating some variables and playing around with some different language constructs and how we can manipulate our various different application bits. Where the hell did that go? There we go. Yeah. Next time, David. You got to make that work next time. So, we will. We're going to make you program in a whole bunch of more languages that you've never seen before. Because I always think that's entertaining for me. Right? If you thought assembly language was weird, be prepared.
Yeah, I thought it was. I was so confusing at times. They seem more easy for me, but everything.
This class is one of those results of what we started to experience as students that didn't have a certain amount of background in some of the things we were working with. And so, we'd get into class 3 and dive into a concept, and half the class would be like, I have no idea what you're talking about right here. So if you bear with me with some of the stuff that's lecture heavy, most of it is about making sure you have some of the concepts or backgrounds so that when Hugo dives into talking about smart pointers and why they're better than regular pointers, you're like, I kind of get why. It's because you don't want to leave the memory that you allocate with memory regular pointers lying around.